Today, I will be discussing the topic of batteries. Batteries store electricity as a form of chemical energy, and they can come in many different forms. You got your standard AAA batteries right here, AA batteries, a 9-volt battery, or as a rechargeable lithium-ion battery. The first invention that resembled a battery came around in 1740, invented by a man named Pieter, who lived in a town called Leyden in the Netherlands. And this invention that he made was called the Leyden jar. A Leyden jar is a glass jar that has aluminum foil wrapped around the outer layer of the glass jar and in the inner layer of the glass jar. There would also be a copper rod that would be inserted into the glass jar that would connect to the inner aluminum foil layer. So here's my rod here. And this copper rod here would be charged by an external voltage source. And this external voltage source you can think of static electricity that you can collect by rubbing wool on your hair, or you can collect the voltage by nature, such as by a thunderstorm, where the lightning bolt would strike this copper rod and charge the aluminum foil that is inside this glass jar. The charge inside this glass jar would be positive. And the positive charges inside the aluminum foil layer of your Leyden jar attracts electrons, which are negatively charged, to the outer foil of your Leyden jar. And those electrons are attracted to the positive charges inside your Leyden jar. And those electrons would come from the external environment that is around and outside the Leyden jar. So for the aluminum foil outside the Leyden jar, it would become negatively charged. And keep in mind, this is possible because this copper rod, which is attached to the inner aluminum layer inside the Leyden jar, is charged by an external voltage source. And the glass of the glass jar separates the positive and negative charges, preventing them from being connected directly. And there is going to be an equal number of charges in the inner foil and in the outer foil. After your Leyden jar is charged, you can connect your inner foil, or this copper rod here, to the outer foil to generate electricity. Or for a Leyden jar, it would generate a huge spark. So you can discharge the Leyden jar by connecting the inner foil to the outer foil. And that's how a Leyden jar works. And this Leyden jar is the earliest instance of the invention of the battery. The construction of the Leyden jar actually acts as a capacitor, where charging the Leyden jar and discharging the Leyden jar is instantaneous. A battery, however, the positive terminal and the negative terminal wouldn't discharge all the electricity in one go. And one thing to note before moving on to the refined version of the battery is that Benjamin Franklin used the Leyden jar to store electricity that came from a lightning bolt. Benjamin Franklin used a key on a kite to attract electricity or the lightning to the copper rod of his Leyden jar. And the important thing to note, let's say I have a battery here, this is my battery, this is my positive terminal, and this is my negative terminal. I'm going to label this as the positive and negative. As you connect the positive terminal to the negative terminal with something in between, say like a light bulb, electrons, which we've talked about is in the outer layer of our Leyden jar, would transfer from the negative side to the positive side. So as I'll write down here. But because Benjamin Franklin emphasized that electricity goes from the positive terminal to the negative terminal, the convention is that current or the electricity would flow from the positive to the negative side. Fast forward to the mid-1800s, we have another invention of the battery called the galvanic battery. And this invention, or at least the idea, was started by a man named Luigi Galvani. And Luigi Galvani studied animal electricity. His discovery was made when Luigi dissected a frog. At one point of his dissection, Luigi Galvani grabbed the scalpel and moved it across the frog's leg. What that frog's leg did was that it twitched. And when Luigi saw this happening, he theorized that nerves or live tissue conducted electrical signals. This one other person, whose name is Alessandro Volta, read through the research reports that Luigi Galvani made and made a disagreement with his theory. Volta claimed that the electricity was coming from the discharge of Luigi's scalpel. So as I'll write down, Alessandro Volta would later prove his counter theory by creating an invention called the voltaic pile. His invention was actually the first true battery since it had a steady and continuous source of current. Alessandro Volta's battery, or his voltaic pile, consists of layers of zinc, copper, and vinegar-soaked fabric cloth. So to draw a picture of this is what Alessandro Volta's battery essentially looks like. And each pattern, or each completed layer, which consists of copper, the vinegar-soaked cloth, and zinc, consists of one cell of the battery. And the new diagram would look like this. And you would get a battery with electricity if you connected your zinc plate with your copper plate. That is separated by the vinegar cloth. Now for a battery to work, a chemical reaction must exist so that there can be a transfer of energy. And this is why if you connect your copper plate directly with your zinc plate, you don't get any electricity at all because no chemical reaction exists. So if it's a copper plate connected directly with my zinc plate, that would equate to no electricity at all. And this is where the electrolyte facilitates the reaction. And you can think of this vinegar cloth as an electrolyte that separates the positive terminal, which in this case is zinc, by my negative terminal, which in this case is copper. Ions, which is spelled as IONS, that are transferred from the zinc plate to the copper plate by the vinegar cloth, that would then allow the electrons that go from the zinc plate to the copper plate. And I'll write this summary down so you can understand it more clearly. And the criteria to select your electrolyte, which here Volta selected the vinegar cloth, is that the electrolyte must maintain a charge balance of your positive ions and the electrolyte must be non-metallic. So to write this down, and your electrolyte must be non-metallic so that the electrons, instead of going through the electrolyte, can be used to power up your home and light up your light bulbs. Here I would have electrons in my zinc plate that would go through a wire going around my electrolyte, going to my copper plate, so my electrons would travel through this wire here. And the ions, which are positively charged, as the negatively charged electrons go through the wire, travels through my vinegar cloth to my copper plate. So my ions, which as my electrons go through the wire, is going to be left in my zinc plate and it'll travel through my vinegar cloth and it'll end up in my copper plate, which I'll draw the ions right here. And the ion charges are determined by the way that the atoms lose or gain electrons to become stable. So I'll write that down. And in order to balance the positively charged zinc ions, your electrolyte, or the vinegar cloth in this case, should be capable of being negatively charged so that the ion charges balance out. I'm going to demonstrate how the chemical reaction works now, but if it's something that you're not interested, I'm going to go ahead and place a timestamp to where you can move on to the next topic of this video, which is batteries in series versus batteries in parallel. Now we will be exploring the chemical reactions that is happening in our galvanic battery, or another way to call it, the voltaic pile. And as you know, the battery has two terminals, a positive terminal and a negative terminal. The positive terminal is called the cathode side, and the negative terminal is called the anode side. So as I'll write down, we have our zinc plate being the anode of our battery, and we have the copper plate being the cathode of our battery. And this is because the electrons are transferred from the zinc plate to the copper plate. And electrons are always going to be transferred from the anode of your battery to the cathode of your battery. But just keep in mind that current goes from cathode to anode. And here I've written down a quick note of what to know. And for the electrolyte, or the material that's between our anode or cathode, is our vinegar-based solution. And the solution that Alessandro Volta used is sulfuric acid. And for this reaction, the copper plate only serves as an electron collector, since in the reaction, the copper atoms is not involved. For the copper plate, its only purpose is to serve as a collector for electrons, as copper is a great conductor of electricity. And for our chemical reactions, there's two different types of reactions that are happening within our battery. One of them is called the oxidation reaction, and the other one is called the reduction reaction. The oxidation reaction is the reaction where electrons are being lost. And our reduction reaction is where our electrons are being gained. And you can think of the oxidation reaction as the process happening in your anode of your battery. And you can think of your reduction reaction as the process that is happening in your cathode of your battery. And remember, a chemical reaction must occur for the battery to work. And this chemical reaction is happening by transferring ions from the anode of your battery to the cathode of your battery. The amount of electrons that can be transferred from our anode to our cathode depends on the excess of electrons, or called the valence electrons, that are on the outer shell of an atom. And if the number of electrons is greater than the number of protons in our atom, we call that a negative ion. But if the number of protons is greater than the number of electrons in our atom, we call that a positive ion. Knowing this fact is also important for understanding rechargeable batteries, where the chemical reactions are reversible. And here's a quick summary of what I said. And the electrons that travel from the anode to the cathode create the voltage difference. Or you can think of it as the electric potential. And you can think of your anode as your high potential and your cathode as your low potential. Now that we have all of these things in mind, I'm going to go ahead and write down what our oxidation reaction is and what our reduction reaction is for each of our terminals of our battery. And our oxidation reaction looks like this. And our reduction reaction looks like this. Now, you might see an annotation that is below your element or your molecular structure symbol. And these can come in three forms. One of them is S, which stands for solid. Another one is AQ, which stands for aqueous, which just means a compound that is dissolved in water. And you have G, which stands for gas. The oxidation and reduction reaction represents what happens as you connect the wire together, as you connect that copper wire together from your anode to your cathode. So recall this is our battery. Say this is our negative side or anode, and this side is our positive side or cathode. If we connect these 2 points together by, say, like a light bulb, then these 2 reactions are occurring. What happens is that for our anode or for our oxidation reaction, we have our zinc atom, which we pretty much have millions in our zinc plate, separated into positively charged zinc ions with a charge number of 2, and separated into 2 electrons. And these 2 electrons has a charge of negative 2. And these positively charged zinc ions would go through our electrolyte. And these electrons would go through our copper wire that would power up this light bulb. And on the other side, we have our positive terminal or cathode. And for a reduction reaction, the electrolyte or the material that's between our anode or cathode is also involved. So just a quick recap of what our electrolyte is. For a reduction reaction, this part here before our arrow represents the reaction that is happening inside the electrolyte, and this result is pretty much the result of this reaction as the electrons and the ions reach our cathode or our positive side. And what's happening is our positive zinc ions is being transferred as positive hydrogen ions. So just to write it down, and this here is pretty much a summary of this side of a reduction reaction equation here. And the sulfate, which is SO4, has a charge of negative 2. And this is important for an electrolyte because it serves to balance out the charges of our ions. And our ion charges are positive 2. And as you recall, the electrolyte must maintain that charge balance electron flow, and thus that makes your battery properly working. You can also combine these 2 chemical reactions together to make a redox reaction. And a redox reaction is basically an overall reaction that you should be expecting that would happen within the battery. And a redox reaction looks like this. And to get to a redox reaction, all I did was cross out common terms that happens before the arrow and after the arrow. So for this case, what I did is crossed out my 2 electron term on each side, and I get my final result. I have our zinc atom that acts as a solid in our zinc plate. I have our 2 hydrogen ions, and they're added together. And on the other side of the arrow, I have my zinc ions and my hydrogen gas, which I have on this side. And for this part here, what essentially happens here is during our chemical reaction, our hydrogen ions is transferring our zinc ions from our anode to our cathode. And the last thing to know about the voltaic pile or the galvanic battery is to know what our voltage difference or what our potential difference is for each cell of our battery. And as you recall, each cell of our battery is just a zinc plate, the vinegar-soaked cloth, and the copper plate, which is considered to be one cell. And we can calculate the potential difference, stated as the electric motive force. You can find it as the voltage potential that's coming from the cathode minus the voltage potential that is coming from the anode. And as you can look up online, the voltage potential difference of my cathode would be 0.34, and the voltage potential difference of my anode is negative 0.76, which then gives me 1.10 volts. So for each cell that I stack like this, and as I connect it together by a piece of copper wire, I get a voltage of 1.10 volts. And if I want a higher voltage, that essentially would be a multiplier of 1.10 volts. I would stack multiple of these cells in series. So if I had another cell, say under here, I would connect this zinc plate to a copper plate. That would be right below right here. So here would be copper. And then the pattern repeats. Copper, your vinegar cloth, which is right here, then a plate of zinc, and the pattern continues. With all that in mind, the battery is going to work. In scenarios where your battery isn't working, there are a few possible reasons that can cause these problems. The first reason can be because that you've short-circuited the battery, making the battery overheat, thus damaging your battery. Another reason can be because that your anode or the negative terminal of your battery has no longer have any electrons to transfer through the wire or any ions to transfer through the electrolyte. And if this happens, that means your chemical reaction stops, thus stopping the battery from working. Another thing that could happen is that your battery is still working, but the voltage that the battery outputs is too low for your application. And another reason that your battery could be dead is that the electrolyte breaks down, or essentially resistance builds up in the battery. And finally, the last major reason could be because that either your anode, cathode, or electrolyte is contaminated. And these could be the major reasons why you would consider your battery to be dead. Now let's talk about batteries in series and batteries in parallel. When you have batteries in series, you always have the positive terminal of one battery connected to the negative terminal of another battery. So the diagram could look something like this. And as you can see, my positive terminal connects to my negative terminal, and my positive terminal connects to my negative terminal, and so on, if you want to connect your batteries in series. And I just put a resistor here just to represent that the batteries will not short circuit. When you have batteries in series, the voltages add up, but it's based on the lowest battery capacity of all your batteries that are in series. So just to write it down, and your battery capacity is measured in amp hours, but usually people would measure it in milliamp hours instead. So let's say this battery here is B1, and this battery here is B2. And B1 has a value of 3 volts, and B2 has a value of 1.5 volts. When we connect B1 and B2 in series, we get the following result, which is just 3 volts plus 1.5 volts. This time, let's say battery 1 has a capacity of 1000 milliamp hours, and battery 2 has a capacity of 2000 milliamp hours. Or resultant battery capacity, when we connect B1 and B2 in series, we would get this result. Because battery 1 has a lower battery capacity, if battery 1 gets completely discharged, what happens is that there would be an open circuit where battery 1 is. So this dot here and this dot here would represent the open circuit, and the circuit would not be complete, and therefore the whole circuit would stop working. And yeah, this is what happens when you stack your batteries in series. Batteries in series, just to mention one more time, you connect your positive terminal to your negative terminal, and you repeat that for any number of batteries that you want in series. Now let's talk about batteries in a parallel configuration. When you have batteries in parallel, you connect the positive side of your battery to another positive side of your battery, and you connect the negative side of your battery to another negative side of your battery. So your configuration, if you connect your batteries in parallel, would look something like this. When you have batteries in parallel, generally what you want to make sure is that the voltages are the same. What happens is that the battery capacity would add up. And for batteries in parallel, the voltages do not add up. It's just the battery capacity that adds up. So let's call this battery A1 and let's call this battery A2. A1 would have a voltage of 3 volts. A2 also has a voltage of 3 volts. But A1 has a battery capacity of 1000 milliamp hours, and battery 2 has a battery capacity of 2000 milliamp hours. And the result, when we put battery A1 and A2 in parallel, is the following. Our output, whether we put a resistor here or a resistor here, would be that we would get 3 volts with a total battery capacity of 3000 milliamp hours. Generally, for batteries in parallel, their energy would be discharged in an equal rate, so that all of the batteries in parallel would eventually run out of power at the same time. Now let's say we have a different scenario. where the voltages of A1 and A2 are different. So I'll go ahead and make a new diagram, and let's call this C1 and this battery C2. And let's give battery C1 and C2 these following parameters. If we wanted to connect C1 and C2 together, we would see a different result. And what would happen is that C1 would attempt to charge C2. What would happen is that their voltages would equalize as battery C1 would attempt to charge battery C2. And once their voltages are equalized, the battery capacity may or may not add up depending how large of a difference the voltages is between C1 and C2. And for C1 and C2 in parallel, if the voltage difference is too high, what would happen is that the battery with the lower voltage would overheat and might even explode. And as I will say in the results, another important note that you should know is that you should know whether your batteries are rechargeable or not. If your batteries are rechargeable, then C1 would charge C2. However, if your batteries are non-rechargeable, C2 would most likely overheat, then either die off or even explode. And commonly rechargeable batteries are lithium-ion batteries, and commonly non-rechargeable batteries are usually alkaline batteries. Whenever you're charging a DC battery, you would always plug the positive side of your other battery to the positive side of the battery that you are charging. And you want to plug in your negative side of your battery that you want to charge to the negative side of your charger. And the voltage difference is usually small. Let's say you have a 9-volt battery here that's at 9 volts that needs to be charged, and you have a battery charger that's at 11.5 volts. In this case, your battery charger, which is 11.5 volts, will charge your battery, which is at 9 volts. And you know your battery is charging once the voltages of both your battery and your charger equalize. And just keep in mind that your battery charger will always have a higher voltage than the battery that you want to charge. And I'll do an on-hands demonstration of batteries in series and batteries in parallel. So for my first demonstration, I have two 9-volt batteries. One of them is a little bit higher than 9 volts, and one of them is lower than 9 volts. And as I'll show you on the multimeter, for this battery, it is 7.9 volts. And for this battery here, it is 9.5 volts. And as we discussed, to put your batteries in series, you would connect your positive side of one battery to the negative side of another battery. So just like this. And our new voltages should add up, which we have a result of 17.4 volts. And the battery capacity of these two added voltages depends on which battery has the lowest capacity. Now for this next demonstration, I'll put these two batteries in parallel. I'll be connecting these two batteries together like this, where the positive side is going to the positive side and the negative side is going to the negative side. Now if I go ahead and measure their voltages now, their voltages would equalize at 9.15 volts. Now be careful when you're doing this with non-rechargeable batteries, as if the voltage difference is too great, the battery that has the lower voltage will most likely overheat and stop working. And if you're using rechargeable batteries like this lithium-ion battery here, charger that you would use, which this battery would snuggle into, would charge this battery at 4.2 volts and also with a current of 500 milliamps. And this voltage difference, as you connect the positive side of your battery to the positive side of the charger and the negative side of your battery to the negative side of your charger, the voltages will then equalize. So here I plug my charger in. If I connect my negative lead to my negative point of my charger and positive to positive, we get 4.21 volts. And if we connect our leads to a battery here, we get 4.091 volts. So as I plug my charger into the outlet, and as I get my multimeter leads out, if I place it between these 2 points, like so, you can see that the voltage of the battery and the voltage of your charger is equalizing. And yeah, that'll do it for this video, and I hope you found this video helpful. Thank you.